Welcome back. Today, we're diving into something incredibly powerful. We're talking about the nuclear chain reaction. It's this super precise, self-sustaining process that unlocks the massive energy hiding inside an atom.
But how does that actually work? I mean, how do you go from one single tiny atomic event to this enormous self-sustaining release of energy? That's the big puzzle we're going to unpack right now.
Okay, so let's start at the very beginning. What is a chain reaction? Honestly, the best way to think about it is like a domino effect, But instead of dominoes, we're talking about atoms. Now, the textbook definition calls it a self-sustaining sequence. And that phrase, self-sustaining, that's everything. It means that once you kick this thing off, it just keeps going on its own. Each step automatically triggers the next one.
So, let's walk through this atomic domino rally. Step 1. A single neutron smacks into a nucleus, let's say a uranium atom. Step 2. That nucleus splits apart. That's fission. And boom! A ton of energy is released. But here's the crucial part. Step 3. That split also lets loose new neutrons. And what do? Step 4. They shoot off and hit other nuclei, starting the whole process all over again. See? A chain reaction.
So let's really dig into how this builds up. And to do that, we have to focus on the real MVP of this whole process, the neutron.
And right away, we hit a pretty big problem. The neutrons that pop out during fission, they are moving at insane speeds. I mean, they're so fast that they just zip right past other nuclei without getting caught. And if they don't get caught, the chain reaction just stops. It fizzles out before it even gets going. So what's the fix? Well, you have to slow them down. This quote right here introduces a fancy word for it, thermalized. It basically just means slowing the neutrons down, kind of like cooling their jets, so they have a much better chance of actually being captured by another nucleus to keep the reaction alive.
Okay, so how is this all done in the real world? Well, it takes a very specific set of tools. You need the right components, and each one has an absolutely critical job.
First up, you need enough fuel. You can't just have a couple of atoms lying around. You need what's called critical mass. Think of it as the minimum amount of stuff, like uranium, that you need to pack into one spot so that those neutrons actually have something to hit. Not enough targets, no reaction.
And remember that speeding neutron problem? Well, here's the solution, the moderator. This is usually something like heavy water or graphite, and its whole job is to act like a set of atomic brakes. It doesn't stop the neutrons, it just slows them down enough so they can be captured easily. Without this, the whole thing just doesn't work.
All right, next you've got all this fuel, you need something to hold it. That's where cladding comes in. It's basically a metal casing, and it does two super important things. One, it gives the fuel rods their physical strength. And two, maybe even more importantly, it traps all the highly radioactive stuff that's created during fission, keeping it safely contained.
So, we know how to get a reaction going, and we know how to make it happen efficiently. But, and this is a big but, the real trick isn't just starting it, it's controlling it. It's all about finding that perfect, delicate balance.
And this is where you can really see that balancing act in action. Think of it like a gas pedal and a brake. The moderator, that's your gas pedal. It slows neutrons down to enable more fission, to make it go. Then you have the control rods. These are the brakes. They're made of stuff that just loves to soak up neutrons. By moving these rods in and out, operators can absorb as many or as few neutrons as they want, effectively throttling the reaction up or down.
And why go to all this trouble? Well, because the goal of a nuclear reactor isn't a massive, uncontrolled explosion. The goal is stability. The whole point, as this quote says, is to get a steady neutron flux rate. Basically, a smooth, constant, predictable flow of energy that we can then use to make electricity.
Which brings us to the final piece of the puzzle. It's kind of the most elegant part of this whole thing, really. It all boils down to one single magic number that defines what a perfectly stable reaction looks like. And that number is 1. That's it, just the number 1. It sounds so simple, right? But everything we've talked about, the critical mass, the moderators, the control rods, their entire purpose is to hit and hold this one perfect number. So what does 1 actually mean here? It's a ratio. For the reaction to be perfectly balanced, for every single parent neutron that starts a fission reaction, exactly one of the new daughter neutrons that flies out is allowed to go on and start another one. Not more, not less, just one. It's a perfect one-for-one replacement, and that is the secret to a controlled, steady power source.
And that leaves us with the big final question, the one at the very heart of all nuclear technology. Achieving that perfect one-to-one balance is a mind-blowing feat of science and engineering. But what happens if you lose that balance? What happens if it's not one-to-one anymore? That single question really sums up both the incredible potential and the immense challenge of unleashing the power of the atom.